Oh, let me pull up another machine so I can make sure that this works, and then ping everyone in the Discord. Yada yada yada. Hello, people of the internet. Okay. We're gonna go over level 6. Let me tell people that, because if you don't tell anybody that. Of course, I don't know how to make links. I can't even see anybody's message. All right. Got them people hyped, hopefully. Twitch.tv, pwn.college, the best channel around, obviously. I understand. Okay, how about this? So you can all hear me now? Can somebody make a comment? Is it good at least? Okay, great. So now I have this stream running on my on my iPad. The problem was my headphones were just switching between my computer and my iPad, because my iPad was playing the Twitch stream and the Twitch stream wanted me to listen to it and go back, but I just paused that. Everything's good. I can see your things. Okay, so to explain what I was gonna explain and talk about, I can see that everyone's kind of stuck on level 6 right now, so we're gonna go over that and try to get close to making a real Linux kernel heap. What I'll say now is, of course, I haven't solved this before. So who knows what's going to happen? It'll be a big learning experience for all of us, but we can dive in here. I'm definitely not going to use the desktop interface. Because I want to be better about this. So let's, and I guess we should do practice mode, because we'll want to end up debugging it and don't want to have to switch over. So let's switch over to our handy dandy practice mode. Some interesting stuff that actually Jan pushed code for this is that your containers now, if we're top, do I not have HTOP? So actually, when your container boots up your security system, because it auto boots the container. Interesting. Anyways, the whole desktop actually now doesn't run when you start a challenge. So if you only use the the SSH mode, you'll actually never stand up the infrastructure and stuff. And yes, as the chat mentions, Jan Infra, we reviewed his code multiple times, or I guess Connor did. I didn't review that code, but Jan's code does make it in, and then eventually we'll fix it and make it better. So, okay, so let's look at this challenge. So we have the kernel image and the kernel module. Let me, in a different thing, downloads, scp hacker at pwn.college / and here's a little trick. If you know you need something in there and it's called a .ko file, you don't know what it is, just slam down put a star in there. Of course, you don't want to put the star in there without the double quotes, because if you put the star in there, your bash shell will try to expand that, which there's nothing there. But this will then yoink down challenge 6, so I can open it up in IDA. File open. I don't care about you. Download challenge 6. All right, so now we got everything in IDA. If you can't see, please let me know. I've tried to increase the font size. Okay, so we have, again, just like all the other stuff, let's walk through what things happen here. So kheap init, so the first thing that happens is it opens flag. When it inits this, it nulls out all of flag. We look, flag is inside, so this is currently residing in our process like this. In our kernel module, not our process, our kernel module. Then we're reading into flag from this file that we opened in the kernel, closing it, cool, so that's where our flag's going to be, creating the kheap proc connection so that we can talk to this in /proc. Then when, as part of the lifecycle, when we open, which means to connect to it, we can see in here, it prints out some stuff. You could go in here and see that this is going to say kheap device opened. Go in here, so this is going to v2 is going to go into private data. So the private data of this is going to be a kmalloc trace. So kmalloc trace, so this is where I don't actually know exactly what this is, but what we're doing is we're going to malloc some data. I think what this is saying is we're going to malloc from a specific cache. So now we are, I believe the previous challenges, I think we were using our own cache. We were like creating our own cache. Here we're using one of the caches supplied by the kernel. This is probably based on the size of the object, but we'll dig into that in a second. But essentially, conceptually, we're allocating something from v2. We're mem setting it 1d0. If I was a betting person, yep, I'd say that is the size, because this 1d0 matches the 1d0 here. Yeah, so thank you for confirming the other challenges where you're using a dedicated cache. Okay, so that's open. So open basically just allocates 1d0 from this cache, and then yoinks it into private data. And then every time, and then I like to go to the reverse. So I like to see what happens when we open, what happens when we release. When we release, it prints out this string, which is going to be device released. Not anything interesting there. We're going to free that private data and null it out. Okay, cool. Now, with this kheap ioctl, so this is where we're doing the bulk of our work. It's going to say device ioctl when we come here. So first we're going to get a local copy of the private data, which then we're going to copy from the users the requests. This is the argument, the request. We can actually, the cool thing is we should be able to look up in here. We know that it's a, hex 30 here, this request. We can properly, but I think the request struct doesn't change. You should already have that, so that should be easier. Okay, great. So copy from user. So from the argument that we pass in, we're going to pass in the argument of the struct in user space. That's going to be copied from user space onto the stack here of kheap request. It'll request hex 10 bytes. So I bet we should be able to find. Yep. Okay, great. And then if the command is 5702 or v5, so if this was an error or the size in request size is greater than 1d0, so we have a limit on what our request size is going to be, return -2. So these are some semantic checks. Looks like if I was a betting man, I'd say this is some optimization that each of these conditions did that, and then the compiler was able to jam them together, but I don't know that for a fact. 5703, frees the private data. 5704 does a k-malloc trace of the same size, 1D0, on, I think this is that same k-malloc cache, and copies the flag onto it. That is interesting. Okay. I had one shape for this, but maybe it's a different one. Otherwise, if the command is 5701, then copy from us onto private data. And then hopefully, since you're doing this so much, you can see what the problem is. So the problem is, let's compare and contrast these. Here we are k-freeing the private data and then setting the private data to 0. We set the private data to 0 so that we don't accidentally reuse this pointer because this data has now been freed. Looking at the ioctl handler, we k-free private data, but we do not modify private data. So we have a use after free. So private data, if we call this 5703 command, will be dangling and will be pointing into some cache where this cache was all the way up in here, and k-malloc caches. And so who knows what that was. So what we can then do, so we know there's a free. The question is then, so when you know there's a use after free, well, we know there's a free and there's a dangling pointer. Now the use part is what we're trying to look for. So the use part here, we look at where this private data is being used. We can actually see with this k-heap release, this is a double free because this is calling free twice. That could be its own vulnerability. So that would be one thing we look at. We look at it in there and be like, oh, actually, we can see that private data is being used here and it's being freed again. That could maybe give us something. However, here we have in this ioctl, just in this function, we can see private data is used here. We're freeing it here. And here at 5701, we are passing in a pointer that's inside of our request struct and the size, so ubuff and size. Then we're copying that into private data. So now we have an overwrite onto private data. So this would be it's a use after free, and what is the use, right? The use here is a write. So we can overwrite data that's there. And what to overwrite? Well, if we, I was going to say we look at the message object. Is there an easier way to do this? Maybe because it's copying, because it copies the flag. String copy as destination, so source dest. So copy the flag into v6. Now, so, okay, there's a couple things that we could do. And also, so we can see that this is actually, the flag is being copied onto v0 after being allocated. So if we free private data, that should go onto the free list. That then can be returned here, and then the flag will be copied. So we'll have private data point to the same thing as the as k-malloc cache. The problem is we need to be able to read that data. So let's go look at the slides and see what we can do. So exploiting the kernel heap protections. I think it was, let's go exploiting the kernel. Bang. Okay, so yeah, so we basically, if we can create a read or write primitive, we should be able to do this and be able to read the flag. So there is, we're talking about two things in here, message. So a message is a struct that's used for IPC messaging. It has a list of a pointer to the head, a message text, a type, this, yeah, so this contains a pointer to messages in the message queue, and this depends the size. So by messing with that, we can, we can see that it's allocated here in the kernel. And this is star message. So this is constructing a message, yeah. So the length can be user controllable. Awesome. And why that length is user controllable is important, because then that will be what the security pointer is. I have no idea. You'd have to read the code. Who knows what that is? But this length being user controllable means that this message we can get it to go into a certain cache that we care about from the kernel, and attack it that way. Okay. So copy message, right? Okay. Copy source +1. So this gets the messages. Yeah, so that's how we get it back. Cool. And a pipe buffer, function pointers. So yeah, cool. All right, and this is probe path, but okay. So let's get to this case. Let's first look up the kmalloc trace, and specifically what I'm interested in is this kmalloc caches. I think I just want to read either the code or the part of the goal of this class is getting used to the code. So we'll look up the code. So kmalloc trace takes a pointer to a mem cache, some flags, and some size. So if you really cared, we could figure out what these flags are, figure out how to parse them into this GFTPT structure, which was actually just right here. So it's just a enum between these, kernel, atomic, high mem, high, which actually I bet we could go here and figure it out. Anyways, this could actually help us figure out exactly what these bits are, but let's go back, and kmalloc trace is here. The definition is, nope, it's used there. It is used there. It is defined here. Oh, and of course it doesn't freaking tell us. Usually what I was looking for was a comment. So usually the kernel is kernels in general are pretty good about doing that here and commenting on their thing. If I was to guess, you're probably not supposed to use directly kmalloc trace, but the compiler, probably whatever we use, compiled down to there. So we can briefly look at this. Let's see, struct kmem cache, GPT flags, size. So taking S, S is this variable. Of course, it's not like actually highlighting S, but it's calling slab alloc node S. So passing in S and the size and the flags, getting ret. It's calling trace kmalloc, and then calling a ksand function, and then just returning that. So what we can see is that this is actually just a wrapper around slub alloc node, and that's defined here. And aha, here we have what I was looking for is comments. Inline fastpass, so that allocation functions have the fastpass folded into their functions. Okay. So it's probably that we called kmem cache alloc, would be my guess, because this would tell you here that kmem cache alloc it takes in a cache and flags, and if we look at what we have here, we have the cache, flags, and size. Interesting. And probably based on this struct, it knows the size. We can see here, so this is the cache to allocate from. Allocate an object from this cache, see kmem cache alloc, cache zalloc for a shortcut of adding the 0. This flag, if I was to guess, the zalloc in this means it's going to zero out the bytes that we get back when we allocate from there. But okay. And then, so under the hood of the fastpass fold into the function, so no function call overhead for requests that can be satisfied on the fastpass. The fastpass works by first checking if the lock list free list can be used. If not, then slub alloc is called for slow processing. Otherwise, simply pick the next object from the lock list free list. Cool. So this is just allocating based on the free list. You can for sure figure out into here. Yeah, so it just allocates it based on this KMM cache. And then going back to our person here, so we can see kmalloc caches 51. Yeah, so that's an extern. I wonder if we can. But whatever, I'm just trying to see if we can find that in there. But this is 51 that it's allocating here with the flag. And this is the private data is also 51. 400cc0. Let's check if those are the same. 400cc0. Okay, yeah, that's great. So this is exactly the same allocation in here. Okay. So let's, I always like to do kernel. Actually, what I like to do now, I used to keep notes in a separate file. Now I like to keep notes in my same exploit script. So, oh, it has to that's got to make the, I can go in here. I think it's running, right? Yeah. Bah. Sometimes I don't actually like using raw tmux directly. I like the other settings in there, but that's okay. Okay, my Emacs is giving me problems. Okay, let's check. BC. Okay, let's go in here. Okay, I can't use tmux, raw tmux. This is gonna drive me crazy. Screen is my go-to. AC. All right. So now we're here in the VM. I guess I probably wanted VM like the other one. But okay, let's get in here. Let's do, okay, so we know that we're going to want to be able to call this free. We have a command for freeing, a command for allocating the flag, and a command to copy from us. Copy from user. So that's copying from us onto the, so we can, so the primitives we have available to us are, yeah. So we really just have this overwrite primitive. We can do a use after free and write. So let's just say, for the sake of argument, that what we wanted to do is going back to Rob's handy slides. What we want to do is to get a message struct the same size. We want that message struct to be allocated in the same cache that we're currently using. So let's, please, will you help me go to okay, this, oh, good, okay. Make a connection, get me my files. Okay. it's not going to be my Emacs. That's why I don't want to do this. But we are in the VM here, so we're definitely not going to run Emacs in this VM. I'm currently doing that. Okay. Okay, Emacs. Okay, and there we go. Now I can switch between them. That's the VM. Here's my code. Okay, so let's do what I was talking about and at least take notes. Okay, so we can free. We can alloc flag onto same cache, and we can overwrite on freed object. So my plan is so like what basically the idea in here is if we control this message, if we control this message size text, like how big the text is, then we would be able to get it to output. So so with the message, if this allows us to control the allocation, so allocate a message that goes into our cache. So that's like one of the first steps. So that's one thing we need to do, allocate that so it goes into our cache. Then we're going to want to overwrite the message. Yeah, think about ASLR, but let's deal with that later. Oh yeah, we have that ASLR break that's in everything now, right? So just the notes, but that doesn't give us a full one. Anyways, overwrite the message, and if we control the pointer, then let's see, in here, copy message. So source. Oh, nice. Okay, there's code for that. Okay, let's look at this real quick. The write-ups for how you're supposed to look at that. Oh, there we go. Levering message. Yeah, I think this is pretty easy, just turning this to a read. Okay. Mod probe. Okay. Yeah, see, create message and a use after free chunk. Yeah, so we need to free a chunk. Yeah, okay, so let's do that. So let's see. The plan is trigger free the private data, allocate a message that goes into our cache. These should be the same pointers now. So we have a message, and a private data. Then we can overwrite the message with whatever we want for profit. Okay. Okay. Oops. No, what is that? What is this? Oh, screen as a password? That's absolutely insane. Sorry, I haven't looked at chat, but I don't think anyone's in here. I think the only person that was here left, so it's just me. Okay. And int main. It's proc k heap if I am recalling it correctly. Yep. Okay. Proc k heap. Let's yoink out some. I like doing some defs. Define. And I like to copy them rather than type them to reduce the chances of a typo. Let's see. Let's say free 5703. And I think I'm good. So I can free, I can copy the flag, and I can copy from us. Okay. Cool. Okay, so let's put the plan into action. So the plan was free the private data. First, I need to connect int open the device. Okay, FD to open the device if FD is less than 0. I do not like that. Okay. Luckily, it's just code. P error open. Wow, the default formatting. I can't remember the format I use, but it's definitely not this. Okay, so we've opened it correctly. Now I need a struct. Okay. Tip def as what did we call this? Kheap request T. If I remember correctly, this request is very simple. It's just first a what should be in here? Shouldn't it be in my local types actually? Now that I look at this, think about this. Local types. What do you look like? Oh, there's a lot of local types. Search. Okay. There we go. Hey. All right, great. We don't have to do anything fancy. We can call this bad boy void star u buff. Size t size. Then we have the exact same one. Let's allocate this on the stack. Request. Okay. And I guess we're actually sending 0 here, so it doesn't matter. So let's null this out. This is a nice way to do zeros. I think I mentioned this last week. Okay, and then free the private data. So we need to make an ioctl int ILCTL, the file descriptor, the command, command free, and then request. I think we're passing in the address. Yep, so we do the address of the address. If ret less than 0. Okay. Okay, free the private data. So now we've freed that. And then we need to, back to our plan. allocate a message that goes into our cache. We'll figure out how to do that in a second. Now, okay, so to do that, we know how to do this. We're at ioctl fd command copy from us. Okay. I bet there's a better way to do this. I'm trying to think of like, because we're not using the functionality where we copy from us, copy the flag. Basically, what I'm thinking is if there's a way we can get data allocated from the same cache somewhere in the kernel that's just a string that we then overwrite the flag with and then read that back out. I think that would be way easier than putting a message on the cache. The reason that this makes me think that is that challenge 7 has messaged the kernel for the win. This one says now we're working on quote real Linux kernel heap. I think this just means we've moved over. So this means we should be able to get other things that allocate there and then overwrite them. So that would be pretty swell. But let's see what we can do. Okay, let's finish this up. If that's 0. Let's see, and let's make sure I got the if defs that I need. Okay. Just getting the using the man page, open 2 to get the exact. I hate not including the right things. All right, I guess we can see if this works. This is our VM. We want another window. GCC. I have pound defines. Oh, 2. Okay. Okay. Why didn't I open? Okay, why is it saying that? I typed F wrong? Okay. Invalidated presupposing brushes and define. How is that invalid? Oh. It's not, I can't do uppercase? It's hilarious. Yep. Man, how picky. One system B. Okay. Type def. Yeah, I messed up the type def. Oops. I want to do an anonymous struct. I think I do something like, yeah, so this is having a struct without a name and just calling it kheap request t. I actually like having struct there so I can know that it is a struct. Okay. All right, now it at least compiles. So we are. But we did the copy. We did the free overwrite the message notes is what we want. But we did copy from us, but our request. Now the question is, how much do we want to overwrite? So let's see. We need to send it something. Request dot. But what we can do is, let's say, character pointer. And we can even cheat. Use a Python A times what was the size that we're dealing with here? Back 1D0. Look at all them A's. Okay, so copy a bunch of A's off there. All right, that will at least overwrite there. Now, this could mess up our kernel because we're writing over some stuff that technically could have gotten allocated. Okay, now we're in here. We'll compile it. Let's make sure Linux in kernel. No, not files. Linux view. Of course, I check on the chat and nobody has bailed me out. Okay. There we go. Yay, sing in action, proc slab info. Thank you, Dolly. All right, sweet. So we have, gosh, we're in a freaking. Okay, so we have a bunch of caches here. So we know that we are in one of these kalloc caches. So these are the sizes, like the max size. So our size was what, 1D0? 1D0, which will fit 1D0, which is at most 464. So that means it's probably going to be in this 512, and kmalloc 512 is my guess. Now, let me see. I believe these numbers are going to be active objects, numbers objects, object size. Okay, great. So I should be able to do this. Grep kmalloc 512. I think it'll be just kmalloc 512, but yeah, I'm guessing it's these guys. We can actually just easily verify this. Kmalloc 512. Okay, so that'll get that. 320. Yeah, we can see it's fairly constant at 320. So whatever I'm doing right now isn't changing it. So if I then, let's see. Oh, okay. We can test this easily by, so we know opening the file should trigger there to be one. So the trick is to call getC to just like get a file, get car, right, from standard input. That way it's waiting for my input. So it will do that once, then free it. So we should go back down. And then overwriting it should probably break things. So maybe I don't want to do this. To compile, go back to the VM. Okay, so we agree. I'm at 320 here. Compile. Of course, now I need another. Why are you beeping at me? Okay, just shut up. Okay, AC, VM connect, and let's get our nice dandy thing here. Copy that. Okay, so we allocated, so we were at 360 or 320. Of course, we see exactly 320 now. Now it should have freed. Still at 320, so. Okay. Okay, I think the overwrite was no bueno. And VM logs. Yep, kernel panic. Oh, cool. Where'd we kernel panic on? Cool. Kernel bug. Probably because we double freed is my guess. Trap free. Cool. Okay. Okay, that was probably for the double free, is my guess. We have to debug it to figure it out, but let's look. Okay, so we were able to do stuff. We need to figure out exactly what cache we're in. So let's do that. Slab info. Okay. Yeah, see, they think it's came out 512. Why wasn't it? Okay. Yeah, okay. Laptop. That's the one I was looking for. Why didn't I freaking... Okay, good. let's see, going to write. Okay, compile it. Okay. And I just had my nice guy, wind turbines. Okay, slab top. Interesting. Oh, it's just like top. Oh, that's crazy. Okay. Info. Ah, interesting. Yeah, well, I'm definitely not compiling that, but now the question is, when I run this thing, which is definitely going to crash it, why? Okay, well, now we'll know why it crashed, because that's... Yeah, so it's going to do it on this exit. The problem is the double free, and that's what's going to kill it. Now our kernel is dead. And okay, so we need to figure out where the heck this allocation is going. Kmalloc caches. And yeah, but how do I figure out which one is that one? There we go. Defined. Slab common. Yes. Size index. We are Kmalloc caches. Great. It's 51. So the 52nd. I guess we should just grep it, figure out what's different there. That would be a nice, easy way to do it. Okay. Okay, this should do an allocation, and then if we do this doesn't make any sense because this KAlexCG64 should be smaller, way too small for our allocation. This open. And one of these zeros, 464, which is smaller than 520. So it definitely can't put it in a 256 cache. It's got to be in here. Okay. That's crazy. So this is just flipping between them. This VMA lock is happening. Wait, are these pages maybe? Yeah, so the number of objects, the object size, the objects per slab. Being prepping for. These are all the ones of size 512. It's got to be either here, 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 or here. Unless there's some other junk that I don't know about, but okay. Well, let's. Okay. Okay, great. There's the struct. Oh, false. Okay, so we can basically find this out from debugging. So let's do that. Nope, no, don't open Discord. Oh no, I gotta go soon. Okay. Yeah, great. Okay, so. Oh shoot! I just killed it. Okay, let's break on open. It's definitely not going to be there, but that's okay. It's still going. Okay. So my idea is what I'm going to do is I'm going to break here. I'm going to see this KL caches that we're using in here so that we can inspect this cache and then figure it out. I think we should be able to quite easily from there do that. And then at least we'll be able to see what cache we're allocating into. Okay, and then What is cool about that? Wait, what? That just my terminal. Whoa, that's crazy. All right, we should hit the breakpoint. So what's this first doing? First is calling print k, so let's step over that. Step over that, and of course, this is going to be a pain, so let's look at all the instructions that are left. Oh. Okay, why does it suck? Okay, nothing's happening. All right, I'll do this, and I'll be done. There we go. Can't tell if that's fine or not. Okay, that's the k heap call. Oof, finally. The k heap call, the print k, and then this is the k alloc trace call. So the second call. So we want to go her, copy. Okay, go, execute more instructions, break, give us that break. Okay, awesome. And then this structure here, this argument in RDI, this is the KMalloc cache that we're doing. Okay, so we can see kind of what that looks like here. We should be able to decode this KMalloc cache, struct KMalloc cache. And where is that struct? Show me the struct. There we go. I wonder if we have that type. If we have the type, you can do cool stuff with it. Flags, blah, 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 blah. Where was the name? It said there was a name. Okay. Okay. Sick. Okay, there we go. That's exactly what I wanted to do. So what I did was I told GDB to interpret that pointer as a as a struct kmemcache pointer, and then to dereference that whole thing. So if you do that, it will interpret it as here. Yay! kmalloc CG512. Boom. So we're able to debug it, figure out that this is indeed, the name of this is kmalloc CG512. We would need to figure out what that is. I don't know what the CG part is. Random kmalloc caches. Oh, Google. Oh, interesting. Okay, I don't know what this CG does, but maybe it says it in here. Kmalloc DMA, kmalloc C group. It's a C group allocation. Interesting. Kmalloc normal. So what we need to do is basically our goal here, now that we know exactly what cache this is allocating into, the easiest way I see to do this challenge, because we have the copy here at the end, and this could be wrong, like I said in the beginning, if you've watched all this way, because we have this ability to copy the flag onto an allocation, onto that wait, I'm not sure what that gets us actually. We can allocate something from the same cache, write the flag. So the flag can be there. We can okay, so we have the private data. One thing okay, something is forming. So if we have private data, can we call kheap free multiple times? It may check that the thing is already not in the list. That's okay if it's been allocated. So let's say, okay, let's say that we can find an object that gets returned to us, some string, right? So here, rather than this, which I think is probably where you need to go in 7, which I guess it's fine if you do it here now, who cares? But an easier approach is basically free the private data, find, first step, find object that comes back to us. So the idea is if we can allocate something directly, some bytes directly into kalloc, this comes back to us in kmalloc CG512. If we can find something that allocates, an object that allocates in there, that the content of that message gets sent back to us, then what we can do is, let's call this object X. And these are just raw bytes. So it needs to be, I don't think strings get allocated in there. I think this is why this may not be the correct approach. But one idea would be free the private data, allocate object X. So now object free data points to that, object X points to there. Then what we can do is free the private data again, which will free X, then do the pointer, the overwrite trigger flag allocation, which will allocate X and copy flag onto it. So that flag allocation will trigger the thing that was just freed, which is the freed private data as a pointer, object X points to it, and now the flag has been allocated and the flag gets copied over and points to this. So now flag is same as X. Now read object X, get flag. This doesn't do anything with the writing part, which was why you made this one. You may need to do that here, but this gives you at least a different path forward. But all right, I think I've done all that I can do today. That was fun. Hopefully it helps. I don't know. Maybe it didn't. Good luck.